It's my great pleasure to introduce Verstraete from here and from Ghent still, right? So Frank kindly agreed to tell us a little bit how quantum groups arise in the study of tensor networks and matrix product operating algebras.
No, thanks a lot. So I'm very happy to have the opportunity to talk to you because many of you are experts in quantum groups, and it seems that what we have been doing in my group since at least 10 years is reinventing lots of quantum groups, and therefore, but I think from a different angle. But okay, this is up to the public to judge because our motivation is probably very different, and that actually really comes from the physics. The physics motivation. So maybe because I have 2 hours now, is this correct? Is this with or without a break?
Up to you.
No, well, you decide. You're the chair, so you decide. I can talk. I can keep on talking.
You want a break in the middle?
Well, if anybody wants a break, just ask. Or wants to leave, please. Because I will have to. I first have to apologize. I'm not a mathematician, so this whole language of C-star algebras, Hopf algebras, all these kind of things. Okay, I'm not speaking that language. Okay, so my background is quantum information, but what we have been quantum computing. But what we have been working in my group for the last, well, for at least 20 years now is to try to understand entanglement in many body systems. Okay, so I think this is if you have to name one tangible thing that came out of the whole field of quantum computation. Okay, so then this is it. Okay, so but this whole field of quantum computation has led to a completely new way of understanding and describing correlations, quantum correlations in many body systems, and it turns out to be very interesting and very complicated to do this, and this is actually where these quantum groups and actually things like category theory and so further will come into play. I'm also happy that Lawrence is there because many of the last papers we wrote are from Lawrence, and Lawrence actually I think is much more better versed in the pure mathematics. But let me, before I start giving somehow the formulas of tensor networks. I don't know to what extent anybody is familiar with tensor networks. I will very briefly sketch what this is about, but let me first give you the motivation. So and actually this is also, I think, for a large extent the motivation of why quantum computers are interesting. So so in physics, basically we know all the equations. Okay, we know to describe the equations, like we can write down Hamiltonians of many body systems. Okay, and typically the rigorous way of doing this is defining a lattice with spins. Okay, so these would be spins. So you would have like basically on every lattice would have a C2. So the Hilbert space would be C2 to the n if you have n spins, and it's easy to write down Hamiltonians for this, like the Hubbard model and many of the kind of things that happen, like the Heisenberg model. But of course, the complexity of finding ground states and understanding somehow the dynamics of systems that are governed by such Hamiltonians is in principle exponentially hard. Okay, and this is many actually of all the breakthroughs in theoretical physics, from my point of view, from a purely physics point of view, in the last 100 years, that have to do with really conceptual breakthroughs or novel ways of understanding how we can approximate that problem. Okay, so it's impossible to do it exactly because the Hilbert space grows exponentially. But like if you look at all the really big breakthroughs in physics, it's all about new ways of approximating that kind of problem in one or the other way. So of course the most famous one is certainly something like Hartree-Fock theory. Okay, Hartree-Fock theory, like if these would be fermionic modes, would be like a variational ansatz in which you have basically a product state ansatz. Okay, and then on top of that you can do perturbation theory. These are exactly the Feynman diagrams. Okay, but these are all very approximate kind of ways of dealing with this many body problem. And actually and it's only due to the advent of quantum computation that people started looking at this problem from the point of view of entanglement. And it turns out that actually entanglement theory is extremely useful to understand somehow the wave functions that arise in these systems. So by the way, so typically these wave functions or these systems, these Hamiltonians, describe electronic degrees of freedom, and from the point of view of electrons, room temperature is very, very small, so we're interested in ground states. Okay, so this is because the typical temperature scale, I'm just saying these things, probably most of you know this, but nevertheless it's good. I find this very relevant information. Like typical temperature scales for fermions are like 10,000 Kelvin, and room temperature is very small. That's why we are interested in finding ground states, very low energy states of Hamiltonians defined on such lattice systems. And of course, typical Hamiltonians are local, so something like nearest neighbor Hamiltonians, Si and Sj. This would be the Heisenberg Hamiltonian. Okay, so it's basically this is Pauli x nearest neighbor ij, xi, xj plus yi, yj plus zi, zj. Okay, so these are the typical kind of cases. Now what happens? So why are these even in one dimensions? Of course, we are interested in this in 1 dimensions, 2 dimensions, and so further. So what actually this quantum information has given is new ways of tackling this problem. Okay, systematic way, and this is in terms of tensor networks. And I will kind of go to this because, of course, this will be at the heart of somehow the reason that we are interested in these quantum group-like structures. But first of all, we have a Hamiltonian, and typically you have a Hamiltonian that is a sum mix of somehow some 2 different type of Hamiltonians. So for example, the most famous Hamiltonian that describes quantum spin system is something like the Ising model. So I have some magnetic field, plus some kind of some constant alpha plus a constant beta times the sum over I, Ci. Okay, so these are Pauli matrices acting on 2 spins, and this is just acting on 1 spin. And what happens if you kind of look at this Hamiltonian, it has something like a phase transition. Okay, so depending on whether alpha or beta is larger or smaller, somehow the ground state changes. Okay, the ground state is either two-fold degenerate or unique. Of course, you have to be very careful with boundary conditions and all this, and we can do this, but let's not, for the sake of study, let's not do this. But anyway, so as a function of, typically you have Hamiltonians, and you have some parameters alpha, beta. In this particular case, of course, I only have 1 parameter because that's only the global factor, but let's assume that you have some gamma times something, another term. And these Hamiltonians have certain symmetries. Okay, so what is the symmetry of this Hamiltonian? For example, the symmetry is in this particular case the product of, let's say, the tensor product over all I of the Zi. Okay, so you see this commutes with this, and all these other terms that you want to do there too. And actually, this is very important. You need symmetries to get interesting physics. Okay, so to get actually phase transitions, to get something like different phase of matter, you need to start from a system with some symmetries. Okay, in higher dimensions, this is not necessarily true because, like in 2 + 1 dimension, you can have intrinsic topological order. But let's, for the sake of simplicity in this talk, limit ourselves to 1-dimensional quantum spin systems. And then you need basically a symmetry. Okay, and the magic, and this is actually what the person to first really understand that symmetries is the key in understanding many body physics, and this is actually both true for quantum and classical physics. But okay, let's focus to classical quantum physics. This started actually with Pierre Curie, but then Landau was the first one to really realize that all different phases of matter are described by the different ways in which the symmetry can be broken. Okay, so this puts basically the representation theory of groups at the center of understanding phase diagrams. Okay, so we would have some different parameters. So it could be something like phase 1, phase 2, phase 3, phase 4. Okay, so we'd have all these different phases. And these different phases, okay, there's generally different kind of behavior that these ground states exhibit would be dictated by different symmetries that are broken or actually different symmetries that are surviving. Okay, so of course, if you only have a Z2 symmetry, so this is Z2, then of course you can only have 2 phases. Okay, you can either break it or not, but for more complicated groups, there's of course many more ways of breaking these symmetries. Okay, and so for a general on-site symmetry, if you have a Hamiltonian that commutes with some kind of a general representation, so of course we work explicitly on a Hilbert space, so we need to kind of explicitly think about the representations of these symmetries. And a global symmetry, this is what we call, if this is 0, we call this a global symmetry. Okay, that means that actually the Hamiltonian commutes with the tensor product of many, always the same kind of object that you do. If this commutes, for example, the Heisenberg model commutes with SU2, Okay, so basically you do a random rotation on every kind of spin. You can easily see that because this is effectively the singlet. This is indeed commuting with somehow the full group SU2. Now what Landau, and actually in much more recent years this has been refined, has realized is that all the different phases of matter are defined. I give you a certain global group G. You have to find all possible subgroups. You have to find two co-cycles, omega, on that subgroup, so this is basically group cohomology on that kind of co-cycle. And then basically you have to define the cosets of G divided by H, and these two co-cycles together with G divided by H are the unique labels of all these different phases of matter. Okay, so basically you have any group, and of course typically we think about finite groups. You have to find all possible subgroups. This will be the symmetry that is remaining. And then actually you can also have some two co-cycle that is related to this. This actually has to do with topological order. Okay, this has to do with the fact that actually this symmetry is realized in a projective way on your Hilbert space. Okay, so this is why you get two co-cycles. So two co-cycles are effectively about projective representations of groups. And the reason that projective representations come up very naturally in quantum physics is that indeed quantum physics is about projective spaces. If I have a wave function and I multiply it with a phase, I have to identify these two wave functions. And therefore, if you have a certain symmetry on a wave function, or on a certain Hilbert space, it does not have to be realized in a way that you don't need that U tensor whatever n acting on psi is equal to psi. It can be up to a phase. Okay, so you can have here e to the I phi. This is effectively the reason why projective representations pop up everywhere in quantum physics. Okay, in this particular case, these are just two co-cycles. So every one of these phases is characterized by one of those kind of objects.
Could you, for example, give us a reference where one can read something about these approaches to phase transitions?
I think there is Tachikawa. Is that the reference for this? There is a reference, but it's difficult to find actually because it's not. This is not. Yeah, Xi-Gang Wen. Yeah, Wen Xi Chen, I think. Xi Chen, Wen, and actually Gu, who is here this week, no? He's coming here, so he might actually be here. So Gu is so Xi-Gang Wen is somebody from MIT, and he had like two very smart students, Xi Chen and Gu, and I think they were really the first ones to understand this. So Gu is actually visiting us this weekend. He's giving a talk on Thursday. So you're all invited, of course. I don't know what he will talk about. Okay, so what is interesting is now, and this is the question that that we try to solve and we're able to basically understand in recent years is there also a way somehow of do these different ground states, okay? Because of course this is not one ground state, no? It's like a whole family. All these Hamiltonians, these are about you change your parameters a little bit, you change your ground state, but there's nothing kind of discontinuous happening. There's some adiabatic way of exploring. So if you have one ground state here, you can adiabatically go to all the other ground states in the same phase. But if you want to go from this to this, something dramatic has to change. And this is either a two co-cycle that changes or a subgroup that changes. And indeed, this is something that cannot happen continuously because you either have a symmetry or you don't. You either have a non-trivial two co-cycle or you don't. And there's the two co-cycles of a finite group or of any group are basically labeled by discrete labels. So there's no continuous way from going from one to the other one. That's why you have a phase transition between these kind of objects. Okay, so what we are interested in is trying to understand the entanglement structure. Okay, so what is the entanglement structure? In the different phases. Okay, so how is the entanglement realized in a different way? Because this turns out to be the key, and also especially in higher dimensions. Okay, so it turns out that this whole kind of framework becomes even much more interesting if you go to 2 dimensions or 3 dimensions, in which you have true topological order, in which there is no, like by just looking at your local density, local reduced density meter, you cannot see anymore that there's some different phase. Okay, all these normally for somehow these 1D phases, these different phases are characterized by different order parameters. Okay, this is the whole concept of Landau. Landau introduced the fact that if you have some kind of symmetry breaking, then of course you can, if you measure an observable that transforms non-trivially according to somehow the different groups, by looking at how your order parameters, okay, your expectation value changes according to somehow multiplying with your group, you can basically distinguish the different phases. This is already kind of only possible for distinguishing the age. Using this, you cannot distinguish the different 2 co-cycles. And in higher dimensions, there's even just something that happens. It's only about basically this topological order. And this thing, this information is purely in the entanglement spectrum. It's basically in what is the entanglement, how is somehow the entanglement realized in these different ground states, this information. That's why this is called topological information. Okay, in this particular case, this has to do with something that people call SPT phases, symmetry protected topological order. And indeed, it's symmetry protected because, of course, all of these things only make sense if you impose symmetries. Okay, so from the moment you don't have symmetries anymore, all of this kind of collapses because there's no group anymore. So basically there's a continuous way of going from 1 to 2 if you allow to break the symmetry. Okay, so in 1 dimension there's basically only one big phase, can continuously go from any phase to any other one, unless you impose symmetries. And from the moment you impose symmetries, you cannot go anymore to these kind of things. Anyway, we are interested in the entanglement structure of these ground states of these different phases, because of these phases are of course defined with respect to the ground states of these systems. Turns out that, so I will kind of first give you the high level picture, and then we'll kind of go to the details. So I will kind of actually go immediately, I will jump to some result that we only have very recently. It's actually a paper that I wrote together with Lawrence. So to understand the entanglement structure, actually, what we need to understand is something that's called dualities. And by the way, okay, because probably some of you are wondering already why, okay, we are not interested in this, we are interested in quantum groups and all this. Turns out that this way in which symmetries can act can be generalized. Okay, and this will automatically come out here. So this way in which the symmetry is acting as a tensor product, at some point you will have to act with the symmetry in a correlated way. Okay, what you do here is not independent on what you do here. They are kind of, you create entanglement by acting with your symmetry. And this is exactly where the quantum groups will come into play. Okay, so this is a kind of a generalization of having these, and this will kind of come up in a very natural way. That's why I'm kind of explaining you this kind of thing. So, okay, so what is a duality for us? Okay, so I have a certain Hamiltonian that consists out of different parts. Okay, so for example, I have this part of my Hamiltonian, I have these kind of terms, so I have a whole bunch of operators with a certain symmetry. Okay, so all these operators, all these local operators have the same global symmetry. Okay, so what is a duality and from our point of view? I give you a whole bunch of these operators, and of course, because they are symmetric, if I multiply 2 of these operators, they also kind of still have the same symmetry. Okay, so they form something like an algebra. Okay, and of course, there's exponentially many of these operators, but nevertheless, I have these structure factors. The sum. I have these structure factors that describe my symmetric local operators. And by the way, please interrupt me now if there's any link or whatever. I think that's the goal. At the end, the goal is really to come with connections. So I hope this will not be a one-way kind of one-way talk. But anyway, so I have these structure factors, and it's not difficult to see. For me, I'm a linear algebra person. I don't know exactly how you justify this actually from the purely mathematical point of view, but that the spectrum of your Hamiltonian is only dependent on these structure factors. Okay, so if I have these operators and my Hamiltonian is a sum of these operators, then you want to know what is the spectrum of this Hamiltonian. In principle, it's enough to know the structure factors. Okay, and the way I see this, but I don't know exactly how to make this from mathematics. Maybe this is a standard result in maths, but it's clear that somehow the whole spectrum in Hamiltonian can be obtained by just doing something like a power method. Okay, you start like you want to find the ground state, you just multiply this thing many, or you take the exponential of minus beta h, and for this, of course, to do this, these operations, the only thing you need to know is how to multiply these kind of things with each other. So if I have two different realizations of the same algebra, these two Hamiltonians will have the same spectrum. Okay, it might actually up to degeneracies. Okay, so there's no guarantee at all that the degeneracies are the same, but at least the spectrum will be the same. If I have an eigenvalue of somehow one Hamiltonian and I have another O alpha O beta is equal to sum over gamma F alpha beta gamma O gamma, then my claim is that, okay, these two Hamiltonians that are built, so I have a Hamiltonian 1 is a sum over x alpha O alpha, H2 is sum x alpha O alpha. My claim is have the same spectrum. I would actually like to understand whether there's a rigorous or this is a standard result or not, but okay, this is certainly true.
So these x alpha, these are just scalars, they're just numbers with their x alpha.
Yes, these are just numbers, so linear combinations of your terms. So in this particular case, for whenever it's an xx term, I have an alpha. If it's a z term, I have a beta. But of course, it can be whatever kind of things. If you look at all the dualities, so in the literature of quantum spin system, there's many dualities now. Okay, so the most famous one is the Jordan-Wigner duality. Okay, that maps spins to fermions, and this is exactly of this form. You basically write down your spin 1/2 kind of algebra. You write down the algebra of your creation and annihilation operators in terms of fermions, and you see that they have the same kind of structure factors, and therefore you say, okay, this is these are dual to each other. Another one is the Kramers-Wanier duality, basically for what is interesting, so for a priori this has nothing to do with dimensionality. Okay, so we are working in a one-dimensional system, but we would like to impose something more to this. We would like to impose that actually so that means you have somehow you can identify O alphas to O alpha tildes. These could be completely different Hilbert spaces. Okay, there's no reason at all. Like indeed, you can have fermions and spins. They can completely different, and it will turn out that they can have completely different symmetries. Where was I? What was I trying to say? So you can have. You would like that if this is local, then this is local. Okay, so you would like that your duality transformation, basically that maps operators here to there, keep locality, okay, because that's something nice. But you don't need this. You don't request this for operators that are not symmetric, because of course if you have an algebra of symmetric operators, you can extend it to also include operators that are not symmetric. For example, in this particular case, you could say, okay, let me kind of look at an operator x at site 1. Okay, this is not in this algebra, but nevertheless, if there is some kind of an intertwiner that relates these two, we'll also kind of relate this object to something in the other theory. And what will happen is that this local non-symmetric object in one theory under such a duality transformation, like a Jordan-Wigner transformation or Kramers-Wanier, becomes non-local. You get a string of kind of objects. Okay, so this is mapped to non-local kind of things. And in this work that was started in the PhD of Lawrence Lotens, so let me kind of write his name. These are the papers to check if you want to understand really the mathematics underlying this kind of object. What was realized is that we can have a full classification of all these possible dual theories to each other if you impose this locality. Okay? And what happens, and this is now where the first time this tensor network notation will come into play. What happens that you can construct explicit intertwiners. Okay, so this will be your theory, let's say, O alpha, and this will be basically the O alpha tilde. Okay, and maybe I should even use different colors here. So these are, principle, these are different Hilbert spaces. Okay, so there's no reason at all that the Hilbert space on the top has the same dimension as the Hilbert space on the bottom.
Right, but they both have this tensor, like global space in both cases has the same tensor product structure.
Well, even that is not true. Okay, so this has a tensor product structure, but because you have like this isospectral property, it's clear that this Hamiltonian must have somehow the same dimension. Okay, so the eigenvectors must live on the same dimension. But if these if these local dimensions are larger than these ones, there's something that doesn't fit. And so what actually will happen is that this space here is a constrained Hilbert space. There will be non-trivial constraints. Okay, so there will be, like, if you know this spin, there will be a constraint on what this spin is. It's basically something like a gauge theory. There are kind of local gauge constraints on what these can. So these are constrained Hilbert spaces. Okay, so I'm not so sure whether this is the right nomenclature for that, but we will give examples of this. But so, of course, for Jordan-Wigner and Kramers-Wanier, this is not the case, and this will turn out because somehow the groups, the symmetries that you consider are just abelian. But from the moment you start looking at non-abelian symmetries, you will kind of map these kind of things to other things. And of course, this goes back in the literature for a very long time. This is these dualities. People have considered this in the context of classical spin systems. So for example, if you have the Heisenberg model here, this turns out to be dual to something that's called the interaction around the phase models. Okay, so in this particular case, these spins live kind of, like this would be spin 1/2. These spins would be just any integer. So it could be any half integers. This could be 0, 1/2, 1, and so further. But there is a constraint, namely that if this spin would be like x, then the next spin is x plus minus 1/2. And then this spin is x plus minus 1/2 plus minus 1/2, and so further. Okay, so this is why it's a constrained Hilbert space. If you know this spin, it's a bit like something like a Fibonacci sequence is also something that will come out of this. If I know somehow that it's spin up, it has to be spin down the next one. But if it's spin down, it can still be spin down. So there's some constraints here. But turns out that, okay, so I will not kind of talk too much about this because this is just to motivate, basically to put everything in perspective, what is going on. Turns out that this gives a complete description of all possible dual theories. Okay, and if you do this for the case of groups, but this is more general because this also works actually for categorical symmetries, but let's stick to the case of groups. So if I have groups, what are all the dualities kind of related? What are all the possible dual theories that I can define if my original theory has a certain symmetry G? Turns out that this is classified by H and G divided by H and by a 2 cocycle over H. Okay, so basically it's HU1. Okay, so this is, so for every possible subgroup and 2 cocycle, you can explicitly construct such an intertwiner. I have not defined this, no? So I will define actually what this is for people that have never heard of tensor networks, but I will kind of do this. And basically well, this is the classification. Okay, so for every one of this, you can find this. And it's of course not a coincidence at all that this is exactly the same classification that you have for phases of matter. Okay, so we see for every kind of the different phases of matter are classified by different subgroups and 2 cocycles. All the possible dualities are described by exactly the same kind of objects. Okay, this is, in principle, these are independent results, but of course this is not at all somehow independent. Okay, so what happens now if you kind of plot this phase diagram again? So have phase 1, 2, 3, and 4. Okay, so for every one of the Hamiltonians in this phase, I can now define 4 different Hamiltonians. Okay, because there's 4 dual ones. So for every one here, in this phase, there's also 4 dual ones, 4 dual ones, 4 dual ones. And what we are able to prove in this recent paper with Laurens Lotens and actually Clément Delcamp is that there's always, in every one of these phases, there's a unique dual theory where all symmetries are broken. Okay, so the interesting thing is that these kind of things are labeled by subgroups and co-cycles, but it's not because the symmetry is broken in one phase that it's broken in the dual phase. On the contrary. Okay, so that's exactly what happens. If you kind of go to these dual theories, that's exactly what, it has the same spectrum, but it changes the degeneracy. Okay, so these dual theories have different symmetries, and there's always in any one of those theories, there's a unique one where all symmetries are broken. Okay, so this is not so easy to prove. This uses something that has to do with bimodule categories. But first of all, you have to ask yourself, what are these symmetries? Okay, so what are the symmetries in these dual models? Because indeed, the symmetries will kind of act in a much more complicated way than in the original kind of theory. Okay, nevertheless, any symmetry here, there's kind of an associated symmetry here, but it will turn out that these symmetries on these dual theories are exactly kind of related to these matrix product operators, which is the main topic, and I think is quantum groups are a special case of such matrix product operator symmetries from my point of view, but that's exactly what we should kind of discuss. Okay, so why is this so interesting and why is this so relevant? As I said, people try to simulate these things. Okay, these are things that people have in the lab. People make systems like that in the lab. People like Emmanuel Bloch with his optical lattices and things like that. People are actually making this and they want to understand the physics of this. You want to understand the phase diagram. You have to simulate this. And the state-of-the-art methods for simulating such spin systems is something that is called tensor networks. Okay, and what is important in tensor networks is what is the amount of entanglement that you have in these systems. Okay, so the fewer entanglement there is, the easier it is to simulate these theories. So, because of what I just said, in every one of these phases, there's a unique dual theory for which all symmetries are broken. This is actually the theory, if you kind of look at the ground states of all these different theories, this is the one that has the smallest entanglement. And how we will represent this with something that is called a matrix product state. And to understand, so this will be some state that acts on this Hilbert space, and to understand at the end the physics that you're interested in, because the physics that you're interested in is the original Hamiltonian that you write down, so it's one of these dual ones. You have to multiply this thing with this intertwiner that is of this matrix product operator form, and basically create somehow degeneracies in the entanglement spectrum. Okay, so that basically makes this bond dimension, which controls the entanglement in your theory, larger by multiplying these different things to each other. Okay, so this is effectively what happens. You increase the entanglement in your system by this, and therefore it's much easier to simulate this theory than the original theory, because in the original theory you have to basically take into account all these extra symmetries that are there that you kind of completely can ignore in the dual theory. Okay, so this has a very practical kind of, our motivation is in some sense very, very practical. Okay, we want to come up with state-of-the-art methods for simulating quantum spin systems. And to understand this, to even understand just the entanglement structure in these different ground states, it turns out that we need to understand these dualities. Okay, because that gives you the optimal way of representing these states with the minimal number of parameters that you have. Okay, so now the question that we want to address is, what are the symmetries in these dual theories? Okay, so maybe let's do it the opposite. Although that's also not ideal. Okay, let's anybody has the same problem. Okay, so this was pure motivation. Okay, so there's no math, but okay, what is the mathematics that we needed to come to this kind of thing? So on the other hand, on one hand, it's actually just all linear algebra. Okay, so there's something. So this whole business of working with tensor networks is linear algebra, but the breakthrough of really understanding the structure of what because we were already working on this for 10 years, and actually the real breakthrough of understanding the symmetries and these dualities and all these things came after talking with the mathematician Jürgen Fuchs and Christoph Schweigert. I don't know if some of you are familiar with them. These are people that have been working on conformal field theories and symmetries in conformal field theories, and they basically discovered the whole concept of bimodule categories. Okay, so they, or at least they discovered that bimodule categories are extremely kind of relevant in the description of the symmetries in CFTs, and actually solved a big open problem, namely the question of writing down all possible modular invariant partition functions. It turns out that this tensor networks give you the representation theory for these bimodule categories. Okay, so basically what we need is these bimodule categories, and let me kind of. So again, I'm not a mathematician. If my students, they read this book of what is the tensor categories? Who is the author of that book? Ettinghoff and company. If I try to read this, I don't understand anything. But my students seem to understand this. And the thing is, if you work with tensor networks, it seems that tensor networks give you the representation theory of these tensor categories. And in that sense, they really, because as a physicist, this is much easier. It's much easier to think in terms of representations than in terms of abstract structures. Okay, and this turns out to be somehow what is happening. But okay, it turns out that the symmetries in these dual models are kind of labeled by the different ways in which you can represent bimodule categories. Okay, so let's actually kind of therefore give a very small kind of, well, of my way of understanding somehow these things. Let me kind of quickly go through this and then try to go to quantum groups. So what is the time? Okay. So bimodule categories are basically the way, okay, let's first look at fusion categories. Okay, so this is a generalization of group theory. Okay, and this is obvious that we need something like group theory. And you have different objects, A, B, and basically this is a sum over C and A, B, C times C. Okay, so it generalizes a group theory in the sense that it's still associative. Okay, this kind of product has to be associative, but you can fuse things to several kind of things. The product of two elements is not unique, can be different kind of things. And there's lots of consistency equations, so there must be unique identity element. So for every object A, there's a unique object B, such that A times B contains the identity, and so further. So there's like this generalizes the normal rules that you have for groups. And the claim is that we can create explicit representations, or that we can basically build a full representation theory of fusion categories in the analogy of the representation theory of groups. Okay, so if this is a group, then the representation theory is, of course, just take any kind of E-rep of G, and then tensor N. This is kind of the way these symmetries are represented on these spin systems. Okay, so we are interested in representing symmetries defined by fusion categories on these spin systems. Okay, so again, if we draw somehow this thing as a tensor product structure, it means that you can embed this dual system into something with the tensor product structure, but it does not mean that every state in that Hilbert space is valid. Okay, so because there could be constraints, like in the Fibonacci case, like you can have an up has to be followed by a down, but then, so this is just that. Okay, so what we are interested in is in generalizing this, kind of how can we do the representation theory of these fusion categories for these particular kind of spaces. And turns out that, well, we do it in the terms of bimodal categories. I think then 5 years after we did this, there was people rephrased all of this in terms of, I think, weak, what is it? But there's lots of adjectives, no? Weak, quasi-triangular, just weak Hopf algebra. I know there's lots of adjectives, but I'm not. Okay, so but it turns out that these tensor networks give you this in a very explicit way. Okay, so basically, what are tensor networks? What we can do is build tensor network representations. Okay, so actually the original way in which we did this was to describe systems in 2 + 1 dimensions. Okay, so not in 1 + 1, but 2-dimensional kind of quantum systems, namely things that people had looked at. These are called string nets. They're very important in the context of error correcting codes. It turns out that these kind of were the symmetries of the entanglement degrees of freedom. But I'm not. So basically, these spin systems can be understood as the objects living at the edge of a two-dimensional theory. Okay, so you have a big two-dimensional spin theory that is gapped. Okay, and these, what we are describing in many ways is basically if I have such a system with a boundary, what kind of Hamiltonians can I have at the boundary? And therefore the symmetries somehow of the bulk are reflected in basically what can happen at the boundary, and these spin systems and these whole phase diagrams and all this is effectively what is the phase somehow diagram of the spin system that can happen at the boundary of your system. But anyway, what are tensor networks? Tensor networks are a specific way of writing down wave functions in this kind of big Hilbert spaces. Okay, so you're probably already familiar with this because some of you, well, I think most of you were here when there were these courses on quantum computing and all this, but okay, so the typical building blocks are tensors like this. Okay, so this is effectively a matrix A, I, alpha, beta. So this would be index alpha, beta. So basically, well, in most cases, this indices alpha and beta have the same dimension, so they basically are a matrix labeled by an index I. That's why we write it like this. Okay, so this is a matrix with indices alpha and beta. Of course, somehow you will have to choose a basis if you kind of put things on a computer and all this. We have to work with the basis. That's typically what we do, but most of the things that we will say are, of course, basis independent. And you have a physical index I, which in the spin 1/2 system, this I would be, for example, 0 or 1. Okay, and a matrix product state is something that is written like this. This is an MPS. And you see, basically, I have this index here shared by this tensor, and that's why you sum over that index. Okay, so we will be interested in things with periodic boundary conditions. Okay, and you can see if I put I1 here, I2, I3, and so further, this is equal to the trace of A, I1 times A, I2 times AI n. Okay, because I sum, so this is a matrix labeled, this is a square matrix labeled by I. So if I fix this label, then basically what I get here is just a product of matrices. And because I close that index, I get the trace of this. And this is called matrix product state. It turns out that all this whole tensor network machinery is based on the fact that indeed using somehow matrices like this, I can effectively represent wave functions on my Hilbert space. So even if my Hilbert space is exponentially large, I have a very kind of easy description of some wave functions at least, because somehow I can just restrict myself to low matrices of, let's say, dimension 10 by 10 or 100 by 100. And somehow the whole wave function is described by this one tensor. And I kind of understand how to extend this. And using actually this formalism, it's pretty easy to see that if you have a wave function like this, you can calculate very efficiently the energy exactly. Okay, because the contraction of such a tensor network can be done. Even this has in principle exponentially many indices, but if you calculate an expectation value, okay, so you have to do this like this. You put the Hamiltonian term here. Basically, this is how you contract, and if you have some boundary, well, if you have no boundary condition, this goes infinity. So basically, how this would be a Hamiltonian term. So this would be the expectation value of one term in your Hamiltonian. And why can you efficiently calculate that if this is your wave function? Because you just start with this matrix, you multiply it with this matrix, and you get somehow a tensor with 4 indices. Then you multiply with this, with this, with this. And you see there's nothing, nowhere do you have something that explodes in terms of number of indices. The number of indices that you kind of have to deal with is never larger than 4 or 5 or something like that. Okay, so that means that there is no exponential cost of dealing with wave functions in this Hilbert space if you represent them like matrix product states.
So matrix product state is the collection of all possible indices of length.
Exactly. Okay, so this is called a uniform matrix product state, and it's in some sense something that is indeed, it should be, well, yeah. Actually, well, we are really interested in the thermodynamic limit. Okay, so these things are actually well defined in the thermodynamic limit, and then the thermodynamic limit, these are called finitely correlated states. And this is something that Vannes, Nachtergaele, and Werner introduced long time ago. Okay, this is now what I.
So sorry to interrupt. So the finite correlation is from when?
Yeah, the finite correlation is that, okay, take an operator here and take an operator here. You see, if I calculate this expectation value, I will have somewhere in the middle, okay, let me kind of put many more spins. I will have something in the middle, if you call this object E. I will have an object E to the power n. And if all these objects are finite matrices, then it turns out you can prove that there's a unique largest eigenvalue in this matrix. This actually follows from something that is a quantum version of Perrin-Frobenius. The second leading eigenvalue of this is finite. It's like strictly smaller than 1. And therefore, if you take a power to the n, this has to decay exponentially. Okay, so this has, E has eigenvalues, let's say lambda 0. This has to be equal to 1, okay, because the norm of your state has to be equal to 1. So the leading eigenvalue of E is guaranteed to be 1. And the second eigenvalue is something like a lambda. And if you calculate an expectation value of an operator here and here, what will happen is that there will be some power of this E that comes in. So this basically will scale like lambda to the n. Okay, so this will scale like lambda to the n. That's all correlation functions have to decay exponentially somehow in the length, and the length scale, the correlation length, is given by the eigenvalues of this. So this is a matrix from these two indices to these two indices.
So the hidden finite system that generates the finite correlatedness is not visible to this.
Okay, so the way Van Nachtergaal and Werner looked at this is that this describes effectively a cavity. So I don't know if anybody of you has ever kind of read about these experiments that Serge Haroche is doing in Paris with cavities. So basically you have a cavity with some atom. So there's some atom with some chi level system. So this is a chi level system. And I have a laser that drives this. Okay, so basically I have a cavity with a laser that drives this, and therefore I have some kind of dynamics in a chi level system. This chi will turn out that this matrices will basically be, so alpha runs from 1 to chi. Okay, so I have a certain atom with chi levels, and I have a laser, and there is light that leaks out of this cavity. And at every time step, there is some kind of, let's say at every kind of integer time step, there is one photon that leaks out. And then, but this photon, of course, was correlated with this atom. And next time, somehow I get a new photon that comes out and so further. And if you look at this wave function of the light that goes out of this cavity, it's exactly kind of described by this type of wave function, in which somehow this A, with the dynamics in your cavity, would basically be reflected in what is exactly this matrix A. It would actually be related to something, a CP map, completely positive map. These are Krauss operators of the CP map and so further. So this is a way, this is basically the way in which Van Nachtergaal and Werner had the physical idea that indeed this is something, a way of generating translation invariant states. And the fact that it's, again, finitely correlated, well, is indeed, well, you see it's something that comes out very, very long time ago. This information is almost gone in the cavity, because the master equation in the cavity, basically the speed of convergence to the thermal state in the cavity is exactly kind of also related to these same eigenvalues. Okay, so there's some kind of so all of these things kind of go.
The E is positive.
Well, this E, okay, so this E, if you write it like this, is the sum over AI tensor A bar I, with AI's Krauss operators. Okay, so effectively, this, if you look at the left or the right eigenvalues of this object, this is equivalent to somehow a master equation. Okay, so because somehow if you put somehow a rho times E, this is equal to the sum over I, AI, rho, AI dagger. Effectively. Okay, so you just multiply from the left with a vector. Let's call this vector a rho, and this is effectively equivalent to this object. And therefore, this is a completely positive map. So there is indeed a relation between these matrix product states and completely positive maps. And actually, the matrix product states that we are interested in are the ones that give rise to ergodic CP maps that have a unique fixed point. Okay, so basically the ones that are that such that this fixed point is full rank and is unique. Okay, these are basically there's all these Perron-Frobenius theorems about this. Actually, there's beautiful lecture notes about this by Michael Wolf in the Technical University in Munich. Okay, so this is what these tensor networks do. This is one dimension, but of course we can easily extend this to higher dimension. Like in the two-dimensional case, these tensor networks, the building blocks are things like this. Okay, so instead of just having 2 legs, we have 4 legs. Now we can glue these things together. And so forth, and this gives us wave functions in 2 dimensions. It turns out all this state of the art. So the magic actually of this whole, and this comes out of the field of quantum information, is that if you kind of make this sky, that the question is how big does this sky have to be such that I can represent any ground state well, okay, so that I have a good fidelity with the possible ground state. And it turns out that actually there's something that is called area laws, that indeed ground states of capped quantum many-body systems all satisfy an area law. And then we worked on this a lot, and then Matthew Hastings worked on this, and we're able to prove that actually these matrix product states effectively form a complete parameterization of the manifold of all possible ground states. Okay, so there's a one-to-one correspondence between these matrix product states and ground states of local Hamiltonians. Okay, they're basically the same thing, and that, of course, makes a huge simplification for understanding and describing quantum spin systems. Because this is, and this chi, the number of chi is actually related to how much entanglement is there. Okay, so you see, to go back to this kind of discussion, this is why we are interested in these, let's say, quantum group type of symmetries. If this has a certain bond dimension here, this will kind of, so it means that this is your A that you need to describe, but a big part of this A is just needed to get the symmetries right, to basically get this duality operator. And the variational degrees of freedom are actually sitting there.
So could you explain, it's probably very easy, I mean, how do I see the difference between usual product states and matrix product states?
Okay, so usual product states, of course I'm talking here about uniform. This would be when this chi is equal to 1. Okay, then there is no correlation at all between the spins. There's no entanglement, so there's correlation, but there's no entanglement between the spins. Okay, so if this guy, so the most famous matrix product state is actually something that was written down by Affleck, Kennedy, Lieb, and Tazaki. And this is when all these AIs, so this is a 3-level system, so D is a 3-level system, so S1, 2, or 3, and the AIs are just the Pauli matrices. Okay, just take the Pauli matrices for the AIs, means that there's a 3-level physical system. The virtual level, you have a 2-level system. These are the Pauli matrices, and this is actually something that's called the AKLT state. This is a very interesting state because it is already something in a phase with a non-trivial 2-cos cycle. Yeah, why is this? It turns out that these Pauli matrices represent a projective representation of Z2 times Z2. Okay, so these models have some Z2 times Z2 symmetry. Okay, and it turns out that these Pauli matrices give you a projective representation of this Z2, of the Z2 by Z2 symmetry, and that's actually why this state is already something that has these non-trivial 2-cos cycles. It's an SPT phase, and this is actually one of the reasons that Haldane got the Nobel Prize, because Duncan Haldane understood all of this. He understood that indeed in this Heisenberg spin 1 model there is some effective topological order and all these kind of things. So this is related to this. Okay, but what we want to come to is not MPSs but MPOs. Okay, because we want to describe the symmetries that all these possible models and especially dual models have. And actually we are interested in all possible symmetries that edges of 2-dimensional quantum spin systems can have. Okay, and these turn out to be not at all related to tensor products anymore. Although they are embedded in a tensor product structure, there's lots of constraints that you need to take into account. What is a matrix product operator? It's exactly the same thing as we had, but now we had acts from one space to another space. Okay, so this is basically just take this leg, but also put it on the other side. Okay, so this is equal to the, if you write it out in components, would be trace I1, J1, I2, J2, and so further. And this would be I1, J1. I2, J2, and so further. Okay, and now we are getting already very, very close to somehow quantum groups. Okay, because it turns out that this tensor here looks very much like an object that you have in a quantum group. Should I?
So what is now I1, J1?
Well, just a matrix.
Many terms.
Or an operator, of course. In general, this could be an infinite dimensional, but it's an operator.
This is J, now you have a matrix.
Exactly. And typically we want this to be uniform again, the same thing. In principle, you can also put some boundary here. Okay, before you take the trace, at the end you can put some boundary. Okay, but this is... Okay, so I talked a bit about tensor networks. We talk about matrix product operators. Well, it will turn out that these matrix product operators form somehow this formless of matrix product operators give you a very systematic way of writing down the representations of these fusion categories. Okay, so these matrix they are used in many different contexts, but we are interested now in using these objects for finding representations of fusion categories. So again, I have A times B is M A, B, C times C. I want to have some object that is independent of the length, okay, because and that's why somehow this delta operator. No, I forgot how it's called in the context of Hopf algebras. The co-product is the one that would probably make that chain longer and longer. So the co-product will be able to define co-products that actually make that chain longer and longer. Okay, that the number of sites.
Just one question. So again, just I think I'm beginning to understand something. So cherish this moment. So what you call the virtual dimension is the kind of dimension where these indices alpha beta are.
Exactly.
Right? Because I mean, in the end, I care about what happens between I and J.
Exactly.
But the way I compute it, I use for this is great.
Indeed. So in the lectures 2 weeks ago, when people wrote down A, B, C, D for your matrix, and they required, and then so basically that's the way. Okay, in quantum groups, what I understood from the lecture. So if you write A, B, C, D down, these are matrices themselves or operators themselves. Okay, so these indices are the I, J indices, and these are the alpha, beta indices. Okay, so it would mean that A11 alpha, beta is equal to A, alpha, beta. Okay, so this is really the connection with how you do it in quantum groups. Okay, and so for example, another object, just already so what was important is that you have this notion of unitarity, that this thing had an antipode. Okay, that you have something like an I star, C star, B star, and D star. You wanted this to be the identity. In our language, what we will need is that I have an A, I will have something like an A star that I define such that this thing is this. This is our kind of way of writing this down. So I think actually this tensor network language I think is very useful also for understanding things like quantum groups. So there's some notion, of course you have to be careful with the order of the indices, but that's, you're basically taking the product, okay, so taking the product of two of these objects in your quantum group was defined as, okay, the new A was A tensor A star plus B tensor B star. You see that this is exactly kind of how you get this, but now the fact that you have the identity, you also have to kind of basically put some object there to, because this is, yeah, this is effectively saying that this thing has an inverse. Okay, that this object, this MPO, has some kind of an inverse. This is the antipode that you get. So all the notions that you had in terms of Hopf algebras for quantum groups, you will be able to kind of define them also for these MPOs.
So, a stupid question. So the entanglement is between the i's and the j's?
No, the entanglement, yeah, okay, but it will turn out to be complicated because so this whole bimodules will actually tell you that if you have a well-defined symmetry that you define in this direction, you can take this tensor, the same tensor, and start building things in this direction too. This will form actually a dual algebra. Okay, so this will form a representation of a dual Morita dual of your fusion category. And that's how you will get the bimodules. Indeed, so you can as well, so normally this entanglement, we are interested in the dimension chi, is effectively what is the dimension of these matrices? This is the amount of entanglement, okay? Because the wave function that we are interested in is like the MPS times an MPO like that thing. And the entanglement is about making a cut in your system like this, so that's why it's this horizontal kind of entanglement. So the bond dimension of your MPO is the one that is relevant. That tells you how much entanglement there is in your system. But okay, I'm just anticipating. If you say the entanglement Pi and J, yes, this is also true because the same object, we can actually stack these things like this on top of each other, find kind of invariant subspaces, and this will define a dual category. Namely, this will be the Morita dual of your kind of object. And this will also form a representation of this kind of thing. So from the point of view, for example, of group theory, these objects would just be representations, okay? So they will multiply according to your group multiplication. These things will multiply according to the EREPs, okay? So we'll kind of multiply according to the fusion rules of the EREPs of your group. This is like, so you can completely understand normal group representation theory in terms of these bimodules, where indeed this thing is not there because they are just normal tensor products, but nevertheless, if you start stacking these things down together like this and taking products, you see that this will kind of give you, so it's not difficult to see that you indeed get the normal representation theory of groups, that this is again a sum of objects like this, and these different objects are kind of labeled by the EREPs that you will have from your different groups, because you take really, well, these indices are not there, so basically what you have here is a U tensor a U. Okay, and then by a Clebsch-Gordon coefficient, you will be able to relate it to this, and this is exactly what will come out of this. Okay, but okay, so anyway, so what we are interested in is finding representations of some, well, this could be a group or of a fusion category, and we want to find the most general way of dealing with this. What is the most general representations of this? Okay, so basically, I want an MPO.
Just one more question. So, when you say fusion category, do you only effectively care about these coefficients, or do you want?
No, of course. I need the F symbols. There's a pentagon equation and all these things. Okay, it must be a consistent. No, of course. So the fusion category is you have these data, but there's also associated with F symbols. Okay, so basically, there's well, we call them zero F symbols, which is related to the pentagon equation, but you will see that this comes out very naturally from this. So in some sense, this, well, it will be part of it will come out of doing the linear algebra basically with these objects. You will see that you get all these conditions in a very natural way. Okay, so I have an MPO labeled by A. Okay, so this means all these kind of just like the group element. So this is a generalization of a group element, no? So of U, say of U of G tensor N. Okay, so this would be U of A tensor N. So all these different matrices are labeled by the same A. And I'm always assuming periodic boundary conditions. And I have the same thing, but all these things are labeled by a B. Okay, and I want this to be an N, A, B, C times, and all these things are labeled by C. Okay, this is exactly what happens in a group. Okay, but here we want the generalization of this in certain sense that this, in which these spaces become kind of thing. Okay, so we want to find all possible solutions to this, and fusion categories, as far as I understand from the purely mathematics point of view, are only well defined if you have a finite number of objects. Okay, so in principle, this should not work for Lie groups or for kind of continuous groups, but our formulas seem to work in the continuous case. Okay, and that's actually what will give rise to quantum groups. So if we do this, and A and B and C are basically labels of SU2, then we will find non-trivial solutions with MPOs with non-trivial bond dimensions that multiply according to SU2. Okay, and this, so globally these objects will, so these will just be the group elements. So this will be globally, this will just look like SU2, but locally these tensors will actually look like SU2 level Q. So basically the quantum group representations. But okay, this is I'm anticipating. Okay, so how do you deal with this? Well, there's one thing that
Q. Where will the print Q be?
Okay, Q will be related, of course, to exactly will be in the 0F. Yeah. So Q, of course, it will be. Okay. So what is the parameter Q? So let's. Well, I will come to this. Okay, because you're asking. What I need to do is to define. I'm interested in Hamiltonians that commute with this MPO. Okay, so how will we get somehow the quantum group out? This will be something that is called the XXZ Hamiltonian, very similar to the Heisenberg Hamiltonian that I wrote down, but with an extra parameter. And you require that this is equal to your Hamiltonian term times this. Namely that you can pull this kind of thing through, that it commutes. If this is locally commuting, then certainly globally it is commuting. Turns out that the Q parameter is here, and defining this, you will see, okay, then these tensors here, they must satisfy some algebraic relations that are related to this parameter Q that is in my Hamiltonian. This is how basically this matrix here, how the Q will enter. Somehow the relation between A, B, C, and D, somehow the way you take products of A, B, C, and D will be related to basically this Hamiltonian. That's how the Q will enter. And then you're interested in the symmetries. Well, for every Q, there will be a different representation, but you need a specific Q because that's the symmetry of your Hamiltonian. You cannot just use that. So these tensors will all depend on Q.
Meaning that you start with the Hamiltonian and then you find the fusion category.
Exactly.
But could you also do the other way around?
Yes, of course. So now that's how we do it. Originally, somehow it was done. Look at the Hamiltonian, find what are somehow these MPOs such that they commute with this. You find also a set of relations between A, B, C, and D, very much like this A times B is equal to Q minus 1 times B times A, and all this. This comes out of this equation. But now, because we have the most general way of writing down symmetries in terms of MPOs, it will turn out that these Hamiltonians are nothing more than the Clebsch-Gordon coefficients of these MPOs. Okay, so that once you have this full MPO characterization, now you can construct any Hamiltonian, all the Hamiltonians that have this as a symmetry. This is effectively the Wigner-Eckert theorem. Okay, so once you have, we were able to generalize the Wigner-Eckert theorem to these MPO symmetries. Effectively, that if you have a local term that commutes with this MPO, then you must be able to write it down as a linear combination of Clebsch-Gordon coefficients. That's effectively the Wigner-Eckert theorem. From this kind of MPO point of view. But where were I? Okay, so there's one thing that a long time ago I called this the fundamental theorem that is actually on which all this is based. Okay, so but it turns out that actually all of this whole formalism, everything that we do is just linear algebra. Okay, so we'll never need more than linear algebra to do this, except maybe if you start from kind of some exotic fusion category for which the F symbols are not known, then you basically have to do more. Then you have to solve for these F symbols, and that's not an easy kind of thing. But anyway, what is the fundamental theorem of MPS or of MPO? It doesn't matter. Okay, the fundamental theorem of MPS tells you that if I have, let's say, well, it's really about psi of A is equal or proportional to psi of B. This is true if and only if there exists something like an x such that x times AI is equal to e to the I phi AI, BI. times x. Okay, again, so what does that mean? So this is an MPS with tensors A, this is an MPS with tensors B. And if this MPS, independent of the length of the chain, is the same as this MPS, this is true if and only if effectively the AI and BI are related by a conjugation with some matrix. And this is of course nothing more than changing the basis in which you define your matrices. Okay, so you can do any, so this is basically BI is x AI x minus 1. Okay, so it's nothing more than changing the basis. It tells you that two MPSs are equal to each other if and only if. So this direction is trivial. If this is equal to this direction is completely trivial to prove. Okay, because, well, all these x's, you have an x, x minus 1, and so forth, they all cancel. But this direction is harder, but it turns out that you can do it with Cauchy-Schwarz. Okay, so there's actually a pretty standard Cauchy-Schwarz argument. No, this x is something that acts on the virtual space. No, so this x, so this AI is a matrix, the chi by chi matrix. So this x has to be an invertible chi by chi matrix. Okay, because these are matrices, so you're basically conjugate. So this is changing the basis in which these MPSs are defined, and of course this shouldn't matter. The basis it doesn't matter because I multiply this with this, and at the end I close my boundary conditions. So this x is, that's why this direction is trivial. This direction is actually non-trivial, but okay, and also not very hard to prove. This is modulo the fact that it's injective. Okay, so what is injectivity for these MPSs? It means that actually all this AI span your full matrix algebra. Okay, so if the AIs start multiplying A1 with A2 and so forth, and you, at some point, if you span the full matrix algebra, then this is injective, and then basically this is true. Okay, so for this particular case, so we wrote a review of modern physics where we explain all of this. Review of modern physics of 2 years ago, together with I only have one review of modern physics, but this is with Ignacio Sirac, David Perez Garcia, Norbert Schuch. So this is where we kind of give all the references there and also explain this. Okay, but it's clear that we need exactly something like this for this. If I want this times this to be a direct sum or a sum of operators like this, I will need this. Okay, so this means that this fundamental theorem is actually the working horse of everything that happens. I think it means that there must exist some object let's call this a 1F symbol. There must exist some object that does that. Okay, so if this MPO times this MPO is a sum of MPOs of this kind, then for every one of these C elements there must exist a 1F. This follows from this fundamental theorem effectively. This is, so again, it's a slight modification of, because now this X is not invertible, but it's effectively the same thing. No? This X, this would be the X. X times this is this times, okay, this object would be the right hand side. So this is the P, this is the A, and this is the B. Okay, but you can prove this, that there must, if this is somehow a representation of that fusion algebra, then there must exist another tensor for which this is true. Okay, and now you can start playing the game. Okay, but if this is true, then of course I can do it like this. But this effectively should be independent of the order in which I do this. Okay, and actually what will come out there is that this is equal to something that's called a 0F. Okay, so this is nothing more, so think about this as the Clebsch-Gordon coefficient. No? So this 1F for a group is nothing more than a Clebsch-Gordon coefficient. Okay, but it's a bit, of course, different because there's this extra indices, and turns out that at the end we will, every one of these lines will be multiple lines and all this, but it doesn't matter. In the bigger picture, this 1F is the Clebsch-Gordon coefficient. Okay, but the Clebsch-Gordon coefficient, if this would be normal group representations, would be completely trivial. Okay, because again, for normal group representations, this line is just one index. Okay, so for a normal group representation, this 1f would just say that if this is A and B, well, this C has to be basically A times B. But now, because these have some dimensions, there's dimensions associated with, I can define something like a Clebsch-Gordon coefficient that tells me that A times B goes to C. Now, if I take 3 of them, basically the order in which I do this should be irrelevant. So there must be, somehow this space should be spanned by somehow there's a 0f. And now if you look at this 0f, there's this famous, the 0f is just coefficients now that depend on A, B, C. This is A, B, C. This would be D, this would be E. This would be F here, F. And this 0f would basically be something that is A, B, C, D, E, F, maybe with some multiplicities and all this. So these are all the indices that are associated to this object. But if this 0f satisfies this, now there's the famous pentagon identity that it has to satisfy. Okay, why? You just start with 4 of them. And you see that there's basically, I don't know if you know this argument, but there's 2 different ways in which you can kind of use these kind of things. So there's one kind of way, there's another way, and this will give me a condition on these 0f's in the sense of 0f times 0f times 0f, a big sum is equal to a 0f times a 0f. Okay, these are the 2 different ways in which you can fuse all these different things together. And this is, I forgot who asked me this is exactly this data that you need for a fusion category. Okay, so this comes out in a very natural way. Okay, so whenever I have an MPO representation of a fusion category, you immediately see that indeed there must be a 0f associated with, and this is the so-called F symbol associated to your fusion category. Okay, so this is the 1f. Actually, these tensors themselves, well, in our papers, like with Jürgen Fuchs and all this, we call this the 2f symbol. Now, it turns out that we want more. We also want that, well, it turns out that this is important for all these dualities, that this is, that there's some, yeah, the duality, so one of the big motivations of all this is about dualities. The duality is actually by turning these indices around. By now saying, if I have an object like this, that satisfies all these rules, if this is a bimodule, then I can also define objects like this, and somehow I can look at invariant subspaces. So I can just take these MPO tensors, stack them like this on top of each other, kind of close them, and I can look at invariant subspaces. Okay, this is a big operator. I can find invariant subspaces here. Okay, so basically I can find what are the injective, so this is basically a sum of typical blocks, but I will kind of associate a label alpha to them. Okay, so once I have found a representation like this, I can stack all of these things like this on top of each other and try to find, okay, is there somehow a way of writing this whole MPO now as a sum of other MPOs? Okay, so these are the invariant subspaces of that algebra here. Okay, so these are basically new operators. Now you turn the whole thing around. No? So the matrices that you had before now become somehow, so instead of kind of working with A, B, C, D, now you basically write them in a different way. Okay, so this is the bimodule. That's why it's actually called bimodules, because you'll have some action that is also kind of acting on the right from this. And anyway, so it turned out that this, for every well-defined kind of theory that you have, for every kind of, so the MPO representations that we find for categories will be exactly the ones for which there's also a non-trivial dual Morita dual kind of description in terms of MPO algebras in this direction. Okay, and this exactly the same object. So terms B, this is something like an A alpha beta gamma times gamma. So I'm not so sure. I think in quantum groups this is probably not something that appears naturally, no? To take your tensors and turn them over 90 degrees. I'm not turning them at all. No, this is really the same tensor, but I'm just reinterpreting them in a different way.
I mean, maybe not. Check
How you do this?
Yeah.
Okay, so this is about the dual. This is also called dual for you, Dan? Okay, but this is, of course, this is a different fusion category. And
Would it be the same as taking the dual picture file quantum group? Right, let's say so, because you have fusion category in object. So would this be the same as a dual quantum group? Yes. So right, it's
yeah, okay.
so there is a duality from a quantum group. You go to a dual. If you do it twice, you come back.
Exactly, this is the same here. Okay, so this like for normal groups, without entanglement, somehow these would be the fusion rules of the ERAPs of your group.
Yeah. So
And anyway, so once you see, okay, this is consistent, then again I can define objects like this. It's equal to, obviously this has to be true, so this is exactly because of the same reasoning as here. We call this the 3F symbols. These are actually the Clebsch-Gordan coefficients. Okay, so normally in terms of normal groups, these are the Clebsch-Gordan coefficients. But exactly, and then of course, once you have Clebsch-Gordan coefficients, you also have 6J symbols. Okay, the 6J symbols are nothing more than these objects. No? Voila. And this is indeed this is the, effectively this is the same reasoning again. Or you can, if you take 3 of them, there's 2 different ways of recoupling them, and they are related by each other by somehow the 6J symbol, and this is effectively the 6J symbol we call the 4F. Okay, so anyway, means that we have not found any representations yet, no? But if this whole thing is consistent, okay, then for this fusion category, I end up with something like a 0F, 1F, 2F, a 3F, and a 4F. Yeah, these are all these equations, all these objects have to satisfy some non-trivial equations. Okay, so this, for example, this pentagon equation that this has to satisfy comes from this. But of course, once you have this 0F, you see basically these objects also have to satisfy something like a pentagon equation. Because this is this times this has to be this times this times this. This is something like a pentagon equation. And it turns out that indeed one solution of all of this is by choosing all these objects equal to each other. That's one solution. In one solution, 0F, 1F, 2F, 3F, and 4F are all equal to the 6J symbols, to basically the 0F symbols. And why is this always a solution? Because we can actually recognize that, well, you can erase this, actually this is irrelevant, that this equation here reduces to the pentagon equation if all these objects are the 0F kind of objects. Okay, the 0, like I said, 0F, the pentagon equation is the product of 3 F's is equal to the product of 2. Turns out if you look, this is how basically we started, how we understood that somehow these MPOs are the key to understanding. So if you kind of look at this equation, I have 2 F's here, I have 2 F's here, but I have 1 0F. But if 0F is equal to basically this 1F, then of course this is something that has 2, has 3 with the sum, and it turns out to be that you can just look at the indices and you can just identify them to each other. So this is nothing more than the pentagon equation. Once this is basically the pentagon equation, and you look at this equation, it also has 2 objects here, 3 objects there. It's also the pentagon equation. It turns out to be exactly the same equation. Same here, all of these things are completely equivalent. So at least we find one solution to this kind of, we can find at least one solution to this, one representation of this fusion is a fusion ring. Okay, one representation of this fusion ring by only using 0Fs. Okay, the whole point, and this is exactly where Jürgen Fuchs and Christoph Schweigert explained this, is that actually any choice of module, okay, that actually this is where the module category will give you a consistent set. Okay, so basically you have your category C, okay, with fusion rules, this NABC, and with somehow pentagon equation. You have to kind of find a module, and you have to define a Morita, a dual category D of your theory. Okay, and basically this module is something, so you have these objects A, B, and so further. Here you have object alpha, beta, and so further with possible fusion rules. And you have also to define objects M, okay, M1, and so further. Okay, the whole point of this bimodule kind of object is that I can act on this module from the left with A. Okay, so I can basically have an action from C to M, and I have an action to the right of M with D. But I cannot multiply the M's with themselves. Okay, this is not defined. I can only kind of multiply them. And this all kind of gives rise to fusion rules. Okay, so there's an object A times an object in M gives me a superposition or sum of other objects in M. Okay, and this is how this one. So if you kind of look at this bimodule structure, and this is something that many people worked out, and I think, well, I'm not so sure where the literature about this, but certainly the reference for us was some paper of Kitaev and Kong, but I don't know exactly whether it appeared before. If you look at the system, somehow the mathematical data that you need to characterize a bimodule category, it's exactly these 5 F symbols, 0, F1, F2, F3, F4, F. All these different associators, somehow that are explicitly represented in terms of these Clebsch-Gordon coefficients here in this language. Okay, and so for every possible module, so given a fusion category T and M, basically there's a unique invertible, there's a unique dual description of this, and this is exactly the one with duals in such a way that this algebra in this direction is also kind of well defined. And okay, so there's a very, well, there's a systematic way of finding this. And if C, for example, is a group, who can guess what the possible modules would have to be? So if C is just a group, so if C is, we call this vec of G. Okay, so what are the possible choices of modules? You have to think about what we said at the beginning of the lecture. Exactly. So all the possible modules are basically labeled by H and 2 co-cycles of this. Okay, so these are all the possible consistent modules that you have for a category vec of G. Okay, so this kind of ties up, of course, exactly with everything that we said before. So okay, these would be the symmetries. Okay, so these, turns out that these MPO algebras for a given choice of M, you look at the MPO algebras defined by these 2 F symbols, these are exactly the symmetries of these dual theories where you chose somehow a particular choice of duality. Okay, so the symmetries of these quantum spin systems, these dual theories, are represented by these MPOs. So how am I doing in terms of time? Okay, so let's maybe be a little bit more.
Just one question. So, in this last statement, when you said that you just go, you started from saying you have a fusion category and you look at MPO representation.
Yes.
And now I'm telling us that any representation, I can realize because I know this. Forgetting about MPO, or do I?
No. Sorry. These are all. Okay. Let me draw. This is exactly what I wanted to do now. So what are at the end? What are these tensors now? How do you label them? What are these different indices that you need for this MPO tensors given a choice of module? So what I'm saying is that you have a fusion category with a certain 0 F symbol. All the possible choices of bimodule representations are given by, let's say, if this is a group, this is H and O squared. For general fusion categories, you can, well, there could be, there's a whole bunch of M's. And for every one of these M's, I can find a different MPO representation. Okay, that's the claim. Okay, and these different MPO representations will turn out to be related to the different symmetries of these, the symmetries in these dual descriptions of the same quantum spin system. But anyway, what are these MPOs? How do you represent them in terms of numbers? Because that's at the end what we do. We put them on the computer. Turns out that all these MPO tensors have a very natural decomposition in terms of 3 line structures. Okay, so the middle index here is labeled by an element in category C. These outer labels are an element in category M. and this middle label is an element in category D. And this is completely consistent with these fusion rules. It basically tells you that if I act with C on M, I get another M. Okay, so the space on which this is defined are all the triples, such that if I act with C on M, I get another M. And there's also the consistency here. If I act from M on the right-hand side with D, I get another M. So the allowed values of somehow this tensor are exactly encoded in the fusion rules of this module, kind of. Okay, so it turns out that this is exactly how these explicit representations work. So there is a kind of a way of identifying now all these different indices to all these solutions, to these 2F. So this is effectively a 2F with lots and lots of indices. And every one of these allowed indices is exactly kind of related to all these different numbers. Okay, so just if you would like to understand this in terms of normal representation theory, the normal group representation theory, this particular case, okay, normal group representations, then this M is equal to vec, so it just contains one object. Okay, and if this is only one object, there's basically no entanglement. Okay, because somehow this is the entanglement is mediated by this M to the next. So this is exactly the thing that gives you the correlated action. So this C would label the group elements. This M is not there, so basically this is nothing more than the normal EREP. It's the EREP that goes from this to this. And what is the dimension of the EREP? It turns out that in this particular case, if I have M times D is equal to a direct sum, basically a sum over M. So it's basically M plus, and the number of times this appears is the dimension of your EREP. Okay, so this is the multiplicity of kind of acting with D on M will give me a multiplicity, and this multiplicity is exactly the dimension of my Hilbert space that I have here. Okay, so the normal group representation theory is just a special case of this. Okay, but all of these things work, and we have explicit kind of ways of representing this and working this out. And actually, I think this was your big frustration of the last 2 weeks, but it finally worked. Last Friday, so Lawrence has been able to kind of construct basically all these possible, just in a black box, given a group, what are all possible dual theories, what are all possible intertwiners, what are all possible NPO symmetries, what are all possible solutions of the pentagon, all these kind of things are completely kind of, in some sense, black box. It's all linear algebra that you have to do. Finding, the key is always finding invariant subspaces. I give you some algebra, find the invariant subspaces of this algebra, so we have constructed very efficient algorithms for kind of dealing with this, and therefore we find basically all these things. Okay, so I've not been able to talk about quantum groups yet. No? So how does all of this relate to quantum groups? Okay, I also don't know. That's why we are here. But at least, this is basically my work during the COVID. I spent weeks and weeks and weeks, and at the end I managed to find a solution of continuous version of this, and I think this is related to quantum groups. So what we would like to do is indeed A times B is equal to N A B C times C. I would like to have an NPO algebra such that if I take the product of two, okay, this is equal to basically this one, but I would like that all these elements are labeled by continuous elements. Okay, so this is something that from the point of view of pure mathematicians is not very well defined, because these bimodal categories, you should only kind of deal with this if you have a finite number of objects. In the case of finite groups, a finite number of finite labels. But here I want these A and B basically to label elements of a Lie group. Okay, so what I try to do is to look at solutions of this for the case of SU2. Okay, so that basically so in this particular case, this was really unique. So I have for any element A and element B, I have a unique element C, such that this is the group. This is just a group multiplication of elements in SU2. And nevertheless, I wanted to have something with a non-trivial bond dimension, something that actually cannot be reduced any further, on which the action is complete. And there is a very famous Hamiltonian that has such a quantum group symmetry. This is called the XXZ Hamiltonian. It's actually something like xi plus 1 plus yi plus 1 plus q minus 1 divided by 2 times zi plus 1. And q has to lie on the unit circle. Okay, so this is, I think, makes it different than the quantum groups that were talked about, but nevertheless it's very similar. Okay, so this is effectively the Hamiltonian. Turns out that, well, you can derive this, but okay, I will not, okay, for people that are interested, I can explain it, but you have to add something like this. Q minus Q1 divided by 2 times Zi minus Zi plus 1. Okay, so this term, if you write down the sum over I, doesn't play any role. Okay, because it's you add it on one side, subtract it on the next side. Okay, so these terms are actually non-Hermitian. Okay, because Q is complex. Q minus 1 is something pure complex. But it doesn't play any role from the point of view of the Hamiltonian. Okay, but anyway, so you can, there's a way of kind of, if you don't know this, there's a perfect kind of consistent way of finding what this is. But we want to, so, and what people knew, this was basically, I think, Saleur and Pasquier. I think this was an old paper. They found that this XXZ model has indeed a quantum group symmetry. Okay, and so how can you derive this from the point of view of this whole language? If there is an MPO, so my claim is that this quantum group symmetries can be represented in terms of MPOs. Okay, so you take this Hamiltonian. Well, actually, let me even explain you how you get this term. Okay, but so if this MPO is a symmetry of that Hamiltonian, then my claim is that then of course you want that this is this plus some object, let's say B times this minus B. Okay, so if an MPO symmetry exists, that is a symmetry of all these local terms, then somehow if I pull this kind of MPO through, okay, so the Hamiltonian to the other side, I must get some telescoping sum. Okay, and you can now say, okay, let's assume that this is right, and now I need my notes because I don't know this by heart.
Before you were telling us that you want an exact commutation, and now you want to have this correction.
Yeah, because, no, okay, I agree. But of course, it turns out, okay, this correction, if you don't want this correction, then you have to add these terms to your Hamiltonian. If you don't want to add this to your Hamiltonian, you see, it's enough, no? If this is true, then the MPO as a global will commute with the global Hamiltonian. Okay, because this is a telescoping sum, so they will all cancel. So that's basically the condition. If you want to, I give you a Hamiltonian, you want to find what are the MPO symmetries, that's how you do it. You write down this equation. Okay, and anyway, this XXZ Hamiltonian is very simple. You write it out, and you see that indeed, if this is equal to this, then this MPO, so if you kind of write this down, this MPO, in terms of, well, like let's do it like we did there. It's A, B, C, and D. Then I have somehow the conditions that A times B is equal to Q minus 1, B times A. A times C is equal to Q minus 1 times CA, and so further. You get somehow BC, CB, and you get a whole bunch of all these equations, exactly like the ones that somehow you normally derive for quantum groups. But this is, so here this comes out of nothing, no? You get this completely for free. I give you this Hamiltonian, of course, I'm using the fact that these very smart people knew already that there's some quantum group symmetry, but nevertheless, it's black box. I give you this Hamiltonian, you want to find what are the MPOs, what are somehow these objects, okay? This is the A00, A01, and so forth. What do they have to satisfy? They have to satisfy a bunch of equations. Okay, and there's also like A times D minus Q minus 1, B times C is equal to the identity, and so forth. There's all this kind of claims. Okay, so now we will restrict ourselves to cases where I can find finite dimensional representations of that algebra. Okay, so I have this algebra that depends on Q now. And I want to, well, for sake of simplicity, actually we don't know what happens if you don't find a finite dimensional representation. So in that particular case, I think you would have to work with MPOs where somehow your virtual degrees of freedom are operators. Okay, but this I'm actually not so sure. What are the, how can you see, given somehow some algebraic equation like this, that there is a finite dimensional representation? But anyway, if Q is an exponential of 2 pi ki divided by 2n plus 1. Okay, so an odd root of unity. Then we were able to construct the following. Then somehow these matrices A, B, C, D, so we can make A equal to, well, let's first define some object. Q is equal to 1 Q squared, and so further. So I think this is actually a standard construction in quantum groups, but okay, I'm not so sure whether this is true or not. But I define and the sigma I define as the permutation matrix, just the cyclic permutations, and the 1. Okay, so these are just the roots of unity and cyclic permutations. And if I define A is equal to X times the identity, this IQ, the B is equal to Y times sigma, C is Z times sigma, and D is equal to A minus 1 plus B A minus 1 C. So I just define these matrices. And I make the MPO with these objects. Okay, so I have basically my continuous degrees of freedom X, Y, and Z here. These are just scalars. X, Y, and Z are scalars. These are matrices. So this is an MPO. This defines an MPO where my physical dimension is 2. So there's a 2-level system here. And here I effectively have, let's take the third root of unity. This would be a 3-dimensional level. Okay, so if I take Q equal to 2n plus 1 is 3, K is equal to 1, and I have 3 objects here. This is a 3 by 3 matrices. This would be an MPO with bond dimension 3. Okay, and so now, what is important, the first thing that you see is I have an MPO like this. You remember somehow the fundamental theorem of MPOs. Okay, so I can multiply with an arbitrary kind of x and x minus 1. I have to identify these objects to each other. Okay, and it turns out that this means that actually, if you do such, if you multiply with x equal to see this, multiply with x is equal to sigma, then the parameters x, y, z are mapped to qx, y, z. Okay, and if you multiply, if you choose x equal to iq, then x, y, z is mapped to x, qy, qz. Okay, so basically what you get is that, of course, these parameters x, y, z are not unique. Okay, it means that if I can identify 2 sets of parameters x, y, z by multiplying them with q. So actually, yeah, just to be sure, what we are trying to do is SL2C, no, not SO. We are doing SL2C, so the complex kind of matrices. Okay, but anyway, so turns out that the way to reconcile this is that indeed, basically, I have to define x is x to the third, y tilde is y to the third, z tilde is z to the third. And if I now define my multiplication x, y, z, and then of course the corresponding t, which is just obtained by requiring that the determinant is 1, so this is uniquely defined by these, times an x. Okay, this gives me x tilde and so further. Okay, so basically I'm assuming that I have the third root of unity. I define these parameters here, x, y, z. I go to x tilde, y tilde, third powers of those, and multiply them according to somehow the normal SL. Then it turns out that indeed this MPO is exactly following these fusion rules. Okay, that actually if I use these MPOs defined by, so this is basically x tilde, y tilde, z tilde, sorry, x, y, z. I have here x prime, y prime, z prime, that this is equal to the same thing with x double prime, y double prime, z double prime. Okay, so using somehow quantum group representations, I've been able to find MPO representations of my group. And actually this is even to people, so this XXZ model, for example, we checked it once. I think there's, you remember how many papers they were written when we checked? 40, so there's 40,000 papers written on the archive with the XXZ model in the title. 40,000. So, and we asked experts, and they all claimed that it had an SU2 level Q symmetry because it has something like a quantum group symmetry, but nobody realized in some sense that this has an SU2 symmetry. Okay, so what we are showing here is that with this MPO symmetries, which are representations of SU2, because the fusion rules that we have are the ones of SU2, not of SU2 level Q. What happens on the virtual dimension here is effectively that we use quantum group symmetry, we use quantum group representations to represent them, but the big difference is that we close these kind of things. And I think this is not a very natural object, maybe in quantum groups, I don't know exactly why, but if you do this, these things form a representation of SU2. Okay, a correlated action, so all these XXZ models actually have an SU2 symmetry. Okay, so these representations of SU2, they are represented in terms of MPOs. Okay, and so in that sense, that's why I was so interested in these. Well, I was so happy that there was a program here on quantum groups. We would like to understand how does that fit? What is this kind of thing to do? Turns out that, for example, if this is an even root of unity, then the product of two of these MPOs is not unique, but is a sum of two different kind of things. Okay, I forgot exactly because it was during COVID, so I have a reason to forget things. But anyway, so the product of two things, if you're even, it's in the paper, it becomes somehow a sum of two different MPOs. Okay, and this really has to do, of course, with well, the fact that, yeah, I don't know exactly, but it has to do with if even or odd gives you different, a different type of representation theory. And so what I would love to see, so this is one example. Okay, it's one example of an NPO algebra that is non-trivial. Okay, it's something, it's very, actually, somebody should complain, oh, how is it possible that this is bond dimension 3 and this is bond dimension 3, that the product of these two is actually something with bond dimension 3. This should not be possible because the entanglement is kind of growing. Well, it turns out that you have to be indeed careful. So you have to, because of this identification, okay, this kind of fact that x, y, z and qx, what you have to take here is actually something that is the direct sum of the three possibilities, because there's basically three possibilities of this. You can have q or q squared. So you have to take a direct sum of all these different possibilities, and then the direct sum times the direct sum of these gives you the direct sum of those, namely number of copies is equal to the dimension squared. So you get many copies of the same kind of thing, but nevertheless it's a representation of SU2. And what we are extremely interested in is indeed trying to understand is that, like, what is the most general way of generalizing this whole framework that I sketched, the bimodule categories, that we understand completely for finite groups, for kind of fusion categories with a finite number of elements. We have complete control now. What would be the analog of this for continuous degrees of freedom? Okay, and it seems that quantum groups in one or the other way fit in. Okay, so this is maybe not the quantum group that you have, and indeed in this representation, I don't know, Lawrence, whether you remember, but for example, this thing, if you take a group here, an element here and here the inverse, then I don't think that this is true. We have to put some other object here. Okay, but not that, I don't know to what extent this is a problem for, let's say, the Hopf algebraic kind of way of representing this. We need, this is not the identity. It's not, you don't multiply these matrices with each other, you have to put something in between. I don't know whether this is a problem or not, but the question is, okay, this is, we have this one example. What about other kind of groups? What about the permutation groups that you guys talked about? What about the easy groups? All these kind of things, they, in one or the other way, you should be able to rephrase them in this language. Okay, so like the representation theory of these permutation groups. As far as I understood, the representation theory is very simple. And it has to do probably with the fact that indeed we allow for arbitrary x's and x minus 1s here. And if you indeed have something like a representation of a permutation group, I was playing around with this like 2 weeks ago when I was in the lecture. It seems that indeed you can decompose this as a direct sums of many things, and it feels that this MPO kind of language gives you a very simple way, I mean not simple, but just an alternative way of deriving many of the results that exist. I think it's useful to think about these quantum groups in this language, specifically because this generalizes to higher dimensions. Okay, so and this is something that I think is still kind of an open problem. How do we deal with quantum groups in higher dimensions? Actually, all of these things that we do here, we understand how they generalize to higher dimensions. So instead of MPOs, what we get is something that is called PEPOs. Okay, so what we get is something like two-dimensional versions of this is this. Okay, so this is the natural generalization of an MPO algebra. So what you get here is a PEPO algebra. From the point of view of fusion categories, this is related to two fusion categories. What we already kind of did, this is again 10 years ago already, we didn't really appreciate or understand what we are doing, but we constructed lots of dualities. Okay, dualities in terms of objects of this kind. Okay, there's dualities from, for example, all these, the toric code to a trivial state. Okay, these are like where you kind of go from states with lots of entanglement to states that have kind of no entanglement, and that map phases to each other. Okay, you map topological phases to trivial phases, topological phases to phases that have symmetry breaking. So you remember somehow in the motivation, this was the whole kind of point of what we are doing. That these MPO symmetries at the end, they arise as the duals of your original thing. So that means that actually, like in the toric code, all these one-form symmetries that you get for people that are familiar with this, they are really kind of the dual symmetries of normal on-site symmetries. Okay, so if you kind of take the duality, this zero, or this normal on-site global symmetries become one-form symmetries, and that's how how you can understand many of these things in these different kind of things. So it seems that's of course also one of the big motivations. Once you understand this language of tensor network, it seems that there's a natural way of defining at least something like a quantum group that would act on somehow two-dimensional kind of system in terms of tensors. But I think I'm overdoing the time allocated here, so maybe there's some more questions.
Thank you very much, Chris. Do we have any more questions? Let me read the lecture, but maybe there's some else.
In the XXC Hamiltonian, Q can be any modules 1.
Yep.
What happens with
Yeah, then I don't know. Then we cannot represent these MPOs, I think, with finite dimension. Okay, then as far as I understand, we need all operators, and that satisfy this set of relations. And it's a mystery to me. I don't know. I don't understand what happens.
This is sort of known that attributes of unity that something
That bigger than at non-root unity. So we think that this is really these objects are sort of representing this center.
So that's why you get classical SU2.
Yes, probably. Then indeed. I think anybody that I talked about, they found this very surprising. That because I wanted to use the paper that we wrote at that time, although I don't think anybody read this paper ever, but I wanted to have as a title, what is the group in a quantum group? Because there's this very famous paper of Fadeev, what is the spin in a spin wave? And Fadeev is also the one who kind of, I think, discovered quantum groups in one or the other way. So I thought this was a good title, but then my co-authors, they thought this was not done. So I'm still very angry that this is not the title.
Well, very common question. Like the fact that you say that, well, some of these relations you would expect, you still have them here, but you have to correct them. Could that be related to the fact that at this root of unity you get rather something a braided quantum group, or no?
But okay, I don't think we worked this out. So there might actually exist a gauge. Lawrence, did we ever check this? I think there might exist a gauge such that this is actually the identity. So that you can do a gauge transform to these objects such that this becomes the identity. I think that should be possible, but I don't think we ever checked that.
translate all the algebras to all algebras.
but in this case, it's quantum group is just the whole algebra. So lots of the properties just one-to-one translates. Right? The picture we draw are just the conditions on the whole. You can make a dictionary, not a language.
But it would certainly, from our point of view, it would be extremely interesting to understand what, like for any compact quantum group, like what are the Hamiltonians that have this symmetry? I think we can do that now. If you kind of understand how to write these easy quantum groups in terms of MPO symmetries, we can calculate the Clebsch-Gordan coefficients, and then any Hamiltonian that is expressed in terms of these generalized Clebsch-Gordan coefficients would have these as a symmetry. I don't think people have done that, and that would be, I think, a very low-hanging fruit that can be done. But again, I'm not so sure that these easy quantum groups, as when I played around with this, it looked like there's always a gauge transform on the virtual level such that these become kind of trivial, that they become direct sums of one-dimensional object. That there is, but I'm not sure about this. So it seems that the easy ones are maybe too easy, but this could be.
There are no more questions, then let us thank Frank again.